So I will shortly introduce the LANCA framework as well as its, let's say, underlying concepts, assuming that you all are familiar with life cycle assessment, so I won't go into those fundamentals. Then I will shortly present two ongoing projects where we deal with further development of LANCA, and I will present you the current status of our development plan, which is mainly that we aim to publish a new version of characterization factors either end of this year or early next year. So basically the land use impact assessment in LCA builds upon a UNEP CTEC project called LULCIA, Land Use and Land Use Change Impact Assessment, and this defines some, let's say, overarching assumptions that hold true and that are agreed upon inside the land use impact assessment field. The two major assumptions are that land use is specified as an elementary flow in the inventory, differentiated in occupation and transformation. So there is an occupation flow in square meter years, and there is a transformation. There's several transformation flows that are quantified through square meters. Basically, you differentiate again between transformation from a specific state and to another state. Then those are the inventory information, and you then use characterization factors similar to other impact categories to quantify the impact on, for example, soil quality. And at the end, you come up with a characterized value for your land use impact. In addition, a set of elementary flows have been defined by the ILCD, which also kind of defines the requirements to any method to be applicable in this framework. So what we did with our LANCA framework that already is now 19 years old, we aligned the available framework to this requirements, and we added, let's say, characterization factors for those flows in place. And at the time being, within the environmental footprint, the soil quality index, SQI, that builds upon the LANCA framework is required to be applied for environmental footprint studies. And it is, again, optional in this case for environmental product declaration according to the current 15804 standard. While this is recommended, it is recommended with the level 2 of confidence, meaning that it's recommended to be used, but with caution. So already in the recommendation, there is a, let's say, hint that this might be necessarily improved. Furthermore, there is, at the time being, no biodiversity method in place. We encounter many feedbacks from especially industry that there is implementation issues as well as interpretation issues with the soil quality index in the environmental footprint pilots. The overall framework, as I said, is based on the UNEP CTEC land use specifications. It is building on a calculation which is based on this figure called the bathtub, where you can see the occupation that is calculated through a quality difference multiplied by the area occupied and the duration of occupation. And then there is two different types of transformation, which first of all is the reversible transformation, which is a kind of artificial assigned time that the land would take to restore. So this is calculated by the regeneration time. And then there is the permanent transformation, which is accounting for the permanent loss of quality due to a specific occupation. The LANCA framework in its current status, version 2.5, presents characterization factors for all the 57 land use flows provided by the LCD for 212 countries and for 5 indicators that I will shortly present next. Those indicators are for the soil quality index normalized and aggregated to a soil quality index. How is the calculation happening? We start with the inventory data, which is, as I said, the land use type, the location, the duration of land use, and the area occupied. This might be, for example, agriculture intensive, which would be the land use type, and then Sweden as a country, and for example, 250 square meter years that are occupied for a specific functional unit. This is what we get from the inventory at the time being. And then there is a characterization step that is happening. And there's 2 different options how this can be applied within the LANCA framework. One is the just assignment with the characterization factor. And the other is a specific calculation of the characterization impact or characterization. And this characterization factors are applied or provided for erosion resistance, for mechanical filtration, for physical chemical filtration, for groundwater replenishment, and for biotic production. We use the inputs and process them, especially using GIS data, and come up then at the end with a characterization factor. Of course, to be applied in current software and database systems for LCA, we have to pre-calculate those values. So what we provide is a characterization factor for each combination of land use type, location, and indicator, and those are statically implemented in the softwares. What is of course needed to calculate the quality difference for those indicators are additional information on soil properties, which especially relate to soil texture, to soil composition, to, for example, distance to groundwater, but also to pH and something else, and some others. And all those are kind of invisible for current LCA practitioners, and they're derived from geo-specific sources. We especially use the harmonized world soil database, but also many other sources to calculate the actual quality difference. What we then provide is a characterized result for all the LANCA indicators for occupation and transformation. Depending on the framework in place, this could also be differentiated in permanent and reversible transformation. And then at the end, what you only see is the single point in the soil quality index, because in the softwares, the implementation that is realized is a black box for all the right-hand side processes. So what you see is you put in your inventory data and you get a single value on quality without a quantification. So it's only points at the end. And what this means is hard to interpret, even though the underlying indicators would be available and would also be available in a non-normalized way. But at the end, this is what is implemented in the EF at the time being. Giving the requests on, let's say, the need, the demand for further development, there is currently 2 ongoing projects that I shortly want to present. First, there is a project that was funded by CEPI. So it's focusing on land use in forestry and EF. And the other one is a Horizon 2020 project called Orienting. But I'll start with the first one, which is already almost finished. We are only waiting for the printing of the final report. In this project, we, together with Sphera and the Wageningen University and Research, had an in-depth investigation on the land use impact assessment in the environmental footprint as applied for forestry systems. including a systematic investigation on potential methodological issues and ambiguities, as well as deriving recommendations for further or for future improvement that try to overcome those issues. Furthermore, we had a very short exemplary application that I will also present soon, showcasing how those improvements could be realized. And then there's a short guidance section for practitioners, as well as a publicly available report. As I said, this should be available very soon, and I can distribute this as well if someone's interested. Regarding the first point, the issues identified have been mainly in the area of the flow nomenclature, as well as the data and the framework itself. In the flow nomenclature, there is a relatively large issue on the, let's say, level of detail of the flow nomenclature itself. Because, for example, in forestry, you would only have forestry and forestry extensive and intensive. And this does not at all reflect the regimes in place, and especially not reflect the silvicultural systems that might differ among countries, but also within countries. And this results in a systematic error, as you only are able to pick up from the few elementary flows available. Then we systematically investigated the data needs and identified data gaps in all steps for the inventory, where there is also a lack of modeling specification definition. Then for the characterization itself, where we recommended some improvements, and then especially during the weighting part for the soil quality index, the weighting and the normalization is done in a one-to-one weighting. So each of the indicators has the same weight, and the normalization is and the internal weighting is done among the 95 confidence interval values among all countries. So there's no, let's say, scientifically or pressure-based weighting in place, but just a statistical one. And then we identified some ambiguities within the unit CTEC framework as it is in place. What we developed then is a new nomenclature based on silvicultural systems for the forestry applications. We present and recommend an improved modeling framework for the inventory to allow to increase comparability and transparency for the input data. We recommended, and we also improved the impact assessment steps. So this is focusing on the LANCA itself, and we improved the characterization model themselves, updating the LANCA indicators as they are, and adding an indicator on human appropriated net primary production that in perspective should replace the biotic production that is in LANCA, and adding a new indicator on soil organic carbon. Here there's a small example on how especially the modeling practices as well as the assumption in the impact assessment, let's say, influence the result. We do a very simple case study on 1 cubic meter of softwood with different modeling approaches in terms of intensity, location, and time frame, as well as the full assessment results on the soil quality index, and some more structured geo-referenced way. So you have here now the results on the EF 3.0 soil quality index, and what you see is that this is really hard to interpret on the one hand, of course, you do have the differences between the numbers, but those numbers ranging from 3,700 to 39,000 do not really, let's say, explain themselves, because you don't have a relation to physical aspects in here, as well as you don't have the differentiation between the underlying contributing indicators from LANCA. What you can see is there's three groups. You have the first three, which is from the Netherlands, an average case, one with a low and a medium management assumption, and one with a high management, which is the highest bar. And for the lower part, you would have one from the Netherlands, which is a specifically calculated foreground system. So the others, all the first four, are calculated for a generic plot, and the Netherlands specific case, so the low impact, is calculated using a specific plot with full rotation that we modeled. So you could see that already during one country, so the first 5 bars, there's large differences in the results. Looking at different management practices, so medium, low, or high management intensity, but also looking at different modeling approaches, which would be the first 4 that relate to, let's say, production volume related modeling for an estimation of the next years, so how much yield will be expected. And the fifth, the low one, would be a full rotation that we modeled over, so occupying the full life cycle of the forest and yielding the overall area. And then the latter 4 would be the same assumptions than the first 4, but looking at Sweden, so a fully different, let's say, geographical situation, as well as soil aspects. This is also definitely reflected in the distribution among locations. So if you look at the current assessment as it is, you would calculate, in this case, the infiltration reduction as an average of the whole country. So you would average in the Netherlands all the low impact areas as well as the high impact areas, just in an area weighted average. But actually, where forestry is taking place is mainly in the red areas, where you would have the higher impact. So looking at the actual land cover, and this is what we recommend here, for a country average characterization factor would, for Netherlands, increase the impact and the characterization factor. Looking at Sweden, you would see that a large share of the country actually is with a forestry land cover, and is therefore relatively close to the full country average characterization factor. Regarding the recommendations for improvement for LANCA itself, I will come up with this at the very end. The second project I want to shortly introduce is Orienting. It's a Horizon 2020 project, started end of last year and will run for another 2 years. It is led by Technalia, supported by VTT, as well as several practitioners, BASF, but also Stora Enso, so a forestry-related company that also has large experience already on environmental footprint. The overall goal is to develop a life cycle sustainability assessment methodology that wants to extend the environmental footprint by economic aspects, by social aspects, but also by criticality and circularity, and furthermore wants to improve the environmental assessment, looking at land use and biodiversity. And this is where we do have our role in the project. So we already did investigate the environmental approaches. The deliverable on that should be available rather soon. It's submitted in June, where we investigated existing biodiversity methods and came up with a systematic recommendation on what to be further developed. The further development takes place in work package 2. This is already ongoing and will be finalized within the next year. There we will update characterization factors for LANCA, looking at biodiversity as well as soil organic carbon, and the biotic production as well as the erosion factors will be improved. Furthermore, a framework considering foreground system information, especially geo-specific information, will be tested in the case studies, which are a tomato production, a bio-based platform chemical, a forestry system, a sheep manure, a sheep wool system, as well as a manufacturing systems distributed all around Europe. And the two indicators that we will propose, or that we will develop, are a new indicator on soil organic carbon, as already said. This builds upon an SOC workshop that we did in the GLAM2 context, and where a joint publication together with the JRC led by Valeria De Laurentiis is already submitted. And this SOC builds upon the same approach that already was in place, developed by Miguel Brandão, and is building on the IPCC's Tier 1 SOC change factors that are assigned to different land use types using the elementary flow list and calculated for an overlaid GIS data source for climate zones and soil types. This is then calculated for the land use types and aggregated using the land cover approach I explained before. The country average values are already calculated and submitted in a publication, and those will be applied and tested within orienting. The second new indicator will be an indicator on biodiversity. There we build upon a methodology called biomass by Stephanie Meyer, which is the result of her PhD thesis, hopefully submitted during the next months. It is a single point on biodiversity based on a multi-scale approach, and what is meant by multi-scale in that method is that we cover in a multiple way the levels of organizational scale. So looking from genes, species to ecosystems. Then we cover the multitude of conservation concepts that are in place. So looking at both proactive and reactive schemes especially. And then of course, taking into consideration the multiple spatial scale aspects, looking from plot level to global scale. This approach is again GIS-based approach, using management practices as well as land use intensity indices to calculate an abstract biodiversity score, and then is mapped again to the elementary flows and provided as country average characterization factors. To be a bit more specific on that, the operationalization is building upon specifying the land use type, as well as, if possible, management parameters. For example, pesticide application or set-aside areas or others. Those are then translated in a land use intensity map, and using the land use intensity index function a characterization map is provided. This allows us to kind of provide 3 levels of characterization. The first one is the one already in place. You would have a country average background characterization factor that is fully consistent with the system in place, so using the elementary flows that we already have. But what we also could do is, as this is a GIS-based system, we could, if, for example, the geolocation of an activity is known, we could provide a grid cell average for foreground characterization. And if primary information is available, for example, on management parameters, it is also possible to adjust the characterization using specific foreground input information that go beyond the inventory that we have in place. How might this be realized? We suggest, and we will apply in orienting, an approach that is called flow property based. So there would be a base flow that is compatible and consistent with the system in place using land use type and country. And then there would be a local information as a flow property that could include intensity, as well as management parameters, as well as geolocation, but in a perspective also includes soil properties, for example. Those calculations would then be realized in GIS and fed back to the LCA system. If I see the time right, I try to catch up a bit and be quick. What we are currently already improving and doing is we're implementing the new aggregation approach as presented. We are including the soil organic carbon as we did it together with the JRC. We are updating the erosion model using a consistent underlying database from the JRC, and we are changing the ceiling factor from a tabular basis to a GIS basis. In the medium future, what we think would be necessary is to get hands on the nomenclature, to make the foreground characterization process applicable, and to include systematically the, let's say, 3 areas of protection that are related to land use, which is on one hand the soil quality, which we have in place, but on the other hand biodiversity and biotic resources, which are currently not really accounted for, and ideally put this together in a weighting based on the cause-effect chain. This is, of course, nothing we can do by ourselves. We see a necessity and a pressure to establish a process to improve this framework, especially in cooperation with the EC or the JRC, but also taking into consideration a multi-stakeholder approach, because of course a lot of stakeholders are interested and do have the need to apply that rather soon. We see a clarifying guidance necessary, especially in EF, and we see some framework aspects that have to be improved, as already said. Thanks a lot.
So I will give a short example of one method to quantify biodiversity in LCA. It's a method published by Chaudhry and Brooks in 2018 from Switzerland. Before I go into that method, I just want to give a short overview of how you can think about biodiversity in LCA. So on your left there, you have your value chain, things that are happening in your chain. You have the life cycle inventory, where you gather all your emissions, use of materials, use of energy, and use of land. And these can be then converted into impact categories like global warming, eutrophication. And here you can have biodiversity as a midpoint indicator. However, biodiversity can also be considered as an endpoint indicator. So then the other environmental impacts like global warming will have an effect on biodiversity, and that you can calculate as an endpoint then. So this Chaudhry and Brooks method, it is a midpoint method. And just shortly on how it how it functions. It's actually very user-friendly and easy to use as an LCA practitioner. So they have done a great job of developing characterization factors. So what you do is you have your inventory where you specify your land use. So in this methodology, you can look at both forests, pasture, cropland, and urban land use. And you categorize what intensity of land use you have, minimal, light, or intensive use. Then you just multiply this with this characterization factor, and then you get your biodiversity footprint. And the characterization factors are developed by looking into a lot of biodiversity data, for example, the Wildfinder database and the red lists. And it's then converted in using a countryside method and combined with the vulnerability score, so that species loss can be more vulnerable in certain parts of the world. So the characterization factors are have a global coverage for 800 something regions in the world. So just to get you a feeling of like what can the results look like if you apply this method. We have started with some studies, and here's the result from a hypothetical study of 1 kilo of beef meats produced in Sweden, Västra Götaland, in Italy in the Po Valley, and Northumberland in the north of England. And as you can see on the y-axis, the metric is biodiversity damage. So it's the potentially disappeared fraction per kilo of beef meats. And here is divided by pasture and by crop production. So you can get a feeling for what is big and what is small in your value chain. You can also, oh yeah, I forgot to say in the previous picture, this is the taxa aggregated unit. So it's like all the like the mammals and the reptiles, sort of like this, weighted together. What you can also do is to get it separated by different taxa. So you have you can get it by mammals, birds, amphibians, reptiles, and plants. So this is a really handy method. However, it has, of course, its drawbacks. And I will mention a few of these. One thing is that it cannot show positive effects. So it's biodiversity damage potential. So the reference situation is an ideal situation without human impact, and everything that humans do is sort of bad for biodiversity. And this can be true, but it can also be not true. For example, in Sweden, we have a lot of high value biodiversity grasslands, which needs human taking care of to maintain the high values. Another drawback is that insects are not included among the taxa groups. And it's also not so handy. It doesn't show so much difference between the different intensity of land use that you can choose from. You had this minimal, intensive, medium land use intensity, but it doesn't show so much of a difference. And this is also because of this reference situation. So the reason is stated in the paper that the reason for the small difference across the 3 intensity levels can be that most species are already wiped out once the natural vegetation of a region is cleared. So it cannot, for example, show, if you want to show the difference between conventional and organic production, it will not, this method would not help you. So as I said, the method is not imperfect, but it's good enough, and for certain applications. So we have just got funding for a 2-year project to start building a database for biodiversity's impacts of food. And in this project, we will collect a large number of data on food production, so country of origin, land use, production method, etc. And we will apply the Shorter and Brooks method to start with. And then it will be flexible for me to maybe apply other methods as they come along. And this project is led by RISE and together with a retailer in Sweden. And for this climate data, for the biodiversity database, we assume the same users will be happy to have this as well. as for the climate database that we also provide. So it's retail, public kitchens and restaurants and so on. Yes, that was very shortly on the Chaudhry and Brooks method and application possibilities.
And I'm going to present some ongoing work that I'm doing with colleagues within this Mestra Digital Forest program that IVL is part of, together with 10 other partners in Sweden, including forest companies. So within this digital forest program, IVL is working mostly with developing different methods for sustainability assessments to fulfill the aim of this Mestra Digital Forest program, which is to increase digital knowledge within the Swedish forest industry. So the aim of this study is to describe a conceptual approach that can be used to assess biodiversity impacts in LCA with a focus on Nordic managed forests using two reference levels. So we focus on two different reference levels. And that is firstly a business as usual reference scenario, which means that the ecosystem quality of the regional current forest management practice is applied as a baseline. But we also explore the use of a target reference situation, which is sort of desired direction for ecosystem management and corresponds to sort of preference stage, such a desired state of biodiversity that could be defined by, for example, political goals or different environmental targets for a specific country. So the purpose of this work is to sort of evaluate the impact on biodiversity based on management choices by individual farmers. And in this work, we build on experience from this conceptual framework for land use impact assessment developed by Untitled. We exemplify this business as usual approach in the end here with examples from 2 regions in Sweden. So as a short background, as we touched upon a little bit earlier here, is that biodiversity is not often included in LCA due to several methodological constraints. For example, there are discussions, which aspects and levels of biodiversity that should be included, and which indicators that should be used to measure biodiversity change, including which scale to measure, local, regional, global. And there are also uncertainties regarding biological response, land use classification, and traceability of supply chains, for example. So the ideal biodiversity indicator would be an indicator that is simple to use and communicate, but also catches sort of this biodiversity complexity. But combining, these 2 aspects is not an easy task. And another thing that is also important to consider is this choice of reference situation, which has an important impact, for example, forestry practices and the quality of biodiversity that is assessed. So as Serina touched upon a little bit earlier here, is this UNEP-CETAC framework that has developed guidelines and a conceptual framework to measure biodiversity for land use impact assessment. And this approach has been developed in different ways since then, as Serena mentioned, but in general, they suggest to use these 6 different land use types and 5 taxonomic groups covering 804 different ecoregions in the world, which means that biodiversity assessments can be made for most environmental contexts globally. However, these ecoregions do not always have sufficiently fine sort of geographical resolution to capture management aspects by individual forest owners, and few studies have sort of tested this global approach for the Nordic and Swedish context. So based on this global approach, we wanted to sort of evaluate how the choice of reference situation and impact assessment methodology provide different options, pathways, and incentives for management options. So in our approach, we search for suitable indicators that could be used to measure and follow up biodiversity aspects with regards to management practices for an individual forest owners. And as a starting point, we found that the existing and established indicator system used within the Swedish environmental quality objective linking forests, focusing on forest structures, were suitable to use. And I will come back to these shortly. The system boundaries were set to cover the total area of forest land under the responsibility of the forest owners. And we also have this landscape perspective, meaning that felling and other silviculture measures are conducted at different timescales, at different times on separate forest stands. And the indicators were allocated evenly on the forest products produced by the forest owners. And we also determined sort of biodiversity indicator, a sort of combined indicator that follows sold and purchased forest-based raw materials and products through the value chain. And in our approach, we selected 2 different reference levels to explore that I mentioned in the beginning. For individual forest owners, the business as usual baseline, which we call UNFCCC baseline midpoint approach, is the mean present quality of state of the ecosystem on a regional level. And this principle is showed in the left figure here. But it could also be the present ecosystem or quality of the surrounding forest owners, which is shown here to the right. And this business as usual approach is quite similar to that used for international climate reporting to the European Union or UNFCCC. And we also selected this target reference level, which describes sort of the desired quality of ecosystems. But such a baseline must be defined by setting a goal-oriented numerical threshold value to address the issue of biodiversity. So the indicators that we apply in this study are established indicators used within the Swedish environmental quality objectives, living forests, and are used by the Swedish Forest Agency as indicators when they follow up biodiversity in the Swedish forests. And the status of the different forest stands is assessed based on 4 different forest structure quality criteria for promoting biodiversity. And those are stands with old trees, stands with dead wood, stands with large trees, and the level of mixed deciduous and coniferous tree species. And the next step of this work was then to calculate the summed value of these indicators and also to calculate characterization factors for the 2 approaches, which I will not have time to show here. But at the end here, I'll just briefly show how this methodology can work in practice with examples from 2 counties in Sweden, Kronoberg and Västernorrland, where calculations has been made for 2 forest owners in each county, using arbitrary values for the areas complying with these 4 biodiversity criteria. So in this table here, we have the sort of reference counties in the 2 columns to the left, and the different forest owners in the 2 counties in the 4 columns to the right here. So what we did here for the forest owner categories was to sort of calculate the summed areas in line 7 that comply with any of the 4 indicators or criteria from line 3 to 6. And then we can get a value in line 8 here of the share of area that comply with the total area by dividing sort of the summed area in line 7 with the productive forest land, which can be seen in the first line here, line 1. And after that, we can calculate characterization factors for wood arriving at the industry, as shown here in line 9 and 10. And we can also estimate biodiversity impact category, IBD here, for the wood delivered to the forest industry, which you can see here in the last line 11. So in this example, the joint performance of the forest owners in Kronoberg is more positive from a biodiversity point of view than the performance of the forest owners in Västernorrland, because it has a more negative value for IBD. Yes, so just to conclude shortly, we suggest a simple approach here to evaluate biodiversity impact for individual forest owners by using already established nationally agreed upon indicators. And our approach focuses on indicators that the forest owners themselves can influence and affect, meaning that there can be an incentive for the forest owners to apply a more sustainable forestry with regard to biodiversity. So the next step of this work will be to evaluate if this method can be used in combination with various remote sensing techniques to develop this methodology further. Thank you.